Following the discussion in our last narrated PowerPoint about the shape of the sampling distribution for sums and averages and the conditions under which we will have a normal curve approximately, we're going to talk about using the normal distribution for problems about sums and averages. These are going to be similar to the week 3 problems using the normal curve, except now we're not looking at questions about the x values themselves, but about sums and averages. So when we're looking at problems about sums and totals, when we know the mean and the standard deviation for the population and the shape is normal curve, we know the expected value of the sum is n times mu. We know the standard deviation of the sum is the square root of n times sigma squared. We did all the algebra earlier to derive these results, and now we can put them to work. So we use this little teaching example with the total weight of 25 airline passengers, and again, credit where credit is due to Moore, McCabe, and Craig. We looked at this already in section 4. We said we knew that the mean weight of the passengers themselves was 190 pounds, including their baggage, and I'm just repeating this in case you didn't watch those earlier narrated PowerPoints. The mean of the total weight for 25 passengers we worked out was simply 25 times 190, or 4750 pounds. And also in our earlier narrations, we said, okay, suppose we think about the standard deviation of the weight, and we said that the standard deviation of the weight of the individual people was 35 pounds. And so based on this, the standard deviation of the total weight of 25 passengers, in order to answer that question, we have to first work with the variance. The variance is n times sigma squared. To get the sigma squared, we have to square the standard deviation. So we've seen this rather large number for the variance, 30,625 pounds squared. Of course, when we take the square root to get the standard deviation, that's about 175 pounds. So now we're going to use these results to answer questions like this in the reader in section 8. What is the probability that the total weight of these passengers is greater than 5,000 pounds? And because we were told that the distribution of the weights is approximately normal curve, we know right away, even though the sample size is only 25, the distribution of the total weights we're working with is going to be approximately normal curve. So we've got the mean is 4750 pounds. We've got the standard deviation is 175 pounds. So all we need to do to answer this question is to say the z-score for 5,000 pounds is going to be 5,000 minus the mean, 4750, divided by the standard deviation of 175. And even though we're now working with standard deviations for a sum or a total and means for a sum or a total, the z-score part works out exactly the same. This is about 250 over 175, a z-score of about 1.43. If we ask Surfstat to help us answer the question, we can see that I've chosen the second picture for the radio button, the area above a specified z. I put in a z of 1.43, clicked the top arrow. It told me that the probability area above 1.43 is about 0.0764. So this is the probability that the total weight is greater than 5,000 pounds. And quite frankly, when you look at this 074, I think you better use a higher weight if you're planning your fuel needed, because on about 7 or 8% of flights, if you looked at your passengers, you might run out of fuel. So again, we're now using a z-score for a total with the corresponding mean and standard deviation. So the ideas from work 3 can help us quite a bit once we set up what the mean and the standard deviation are. So that's a problem about a sum or a total. Problems about averages, again when the mean and standard deviation are known and the shape of the sampling distribution is normal curve, rely on the facts that the expected value of the average x bar is the population mean mu, and the standard deviation of x bar is sigma over root n. So once we have those facts, here's the illustration using heights of men from a university population. The source where I took this problem gave us 3 important facts. The distribution of heights for this restricted population is close to a normal curve with the mean mu of 70.0 inches and a standard deviation sigma of 2.8 inches. So if we asked a question like this is a week 3 question. What is the probability that a man selected at random from this population has a height less than 68 inches? Using the ideas from last week, for an individual, the z-score is going to be 68 minus 70 over 2.8. This individual is going to have a negative z-score because they're 2 inches below the population mean. The z-score is about minus 0.71. So if we use Surstat or Stata or the table in this case, the area below a minus 0.71 is about 0.2389, or we might round it to about 0.24. So in contrast to this, let's consider a random sample of size 50 from this population. And again, we're going to work out the important facts about the distribution of x bar. The distribution of x bar is going to be close to a normal curve. Why? Because the distribution of heights is, so we know that'll work for any sample size. The mean of x bar is also 70.0 inches, but the standard deviation of x bar, now we need to do the sigma over square root of n. So now for x bar, the standard deviation is 2.8 divided by the square root of 50, about 0.396 inches. So now let's look at the question. What is the probability that a simple random sample from this population of size 50 has an x bar less than 68 inches? So this time we're making a z-score for x bar, and so we're still looking at 68 as the number we're interested in, but now it's for x bar. So minus the mean 70, but this time when we're doing a z-score for x bar, we divide by the 0.396. So we get minus 2 over 0.396, and so we get a z-score of a little less than minus 5. That's a very low z-score. If you try to find an area, you can't even use the table in Baldi and Moore, because this one is quite literally off the charts. It's a very small probability. Using some tricks in Stata, it's about 22 in 1 billion. So go back and look at this. Whether we're asking a question about an individual's height or we're asking about the behavior of an x bar from a simple random sample of size 50, we get very different answers. Now there's one more thing we can do with this kind of example. That's a question again about a distribution of x bar. So it will go something like this. What sample size would be needed so that 99.7% of all possible samples give an average that is within half an inch of the population mean? Now if we do this a little bit informally using the 68, 95, 99.7 rule, we need to find what the sample size is so that 3 times 2.8 over the square root of n is equal to half an inch, because that would give us 99.7% of all the X bars within half an inch either side of the mean of 70. Okay, so we're going to set up this equation. 0.5, half an inch, is 3 times 2.8 over the square root of n. Warm up your algebra skills. The square root of n is 3 times 2.8 over 0.5. Be sure at this point you square the 3 times 2.8 over 0.5 squared. You get n is about 281.11, and when we're solving for sample sizes, we'll always round up. So we will say that in order to get a pretty good guarantee that a sample X bar will be within half an inch of the mean, we're going to need a sample of size 282. So these kinds of problems working with distributions of X bar are actually going to be really important in the work coming up in weeks 5, 6, and 7. And so we're taking the time in week 4 to build a really good foundation about solving X bar problems.